So up until this point we've talked about how velocity is a change in position over a change in time, and then now we're going to kind of ask ourselves what happens when the velocity changes. Well, we all know that if our velocity is initially 0 at a stoplight and we stomp on the gas pedal, then we're going to accelerate. So acceleration is going to be a change in velocity. Now this was initially formulated by this fellow named Galileo, who was trying to understand how things fell, but he didn't have a fine enough timing system to be able to make some good measurements. So actually what he did was he used inclined planes, and one of the things that he kind of reasoned is if you have a ball like this and it's rolling down a ramp, then the slope is kind of downwards, and he noticed that, well, the ball sped up, and then what he did is he had a sloped upwards, and he kind of sent the ball up like that. He noticed that the speed decreased, and so in this case it would be accelerating. In this case it would be accelerating in the negative direction, and he kind of reasoned that if you had something exactly between there and there, well, would you expect the slope to change? Would you expect the speed to change? Well, the answer would be no. I have a little demonstration on this. So you can see if I roll the ball down the ramp, the velocity does indeed increase, so it's accelerating. If I go up the ramp, the speed actually decreases and actually is going to go in the negative direction. And if I go across a level plane, the speed, velocity stays the same. Now what this kind of leads us to is a basic definition of acceleration, which is going to be a change in velocity per unit time. Or we could say acceleration is going to be equal to velocity over time, kind of for shorthand. And we all know that I love units, so velocity is going to be a meter per second, and if you divide that by a second, then we're left with a meter per second squared. So if you ever see the unit of a meter per second squared, you know we're talking about an acceleration. And we can also kind of rearrange this guy to say that the velocity could be equal to the acceleration times time. Now, examples of this: suppose you're sitting at a stoplight and your speed is initially 0, and then you stomp on the gas and your speed is initially some very large number in this direction right there, then yes, you've definitely accelerated. Now let's consider a case where you've got a speed maybe of 10 miles per hour and you come to a stop. Then, well, look at this, your speed has indeed changed. It's gone from 10 to 0. So here you've accelerated and your acceleration is going to be positive. Here you've accelerated, but now your acceleration is actually going to be in that direction. And if we call this direction positive and this direction negative, then your acceleration would be negative, so you've decelerated. You've accelerated in the negative direction. Another thing to kind of consider is suppose you had a speed and that speed was in this direction, and at some later time you happen to be going in this direction. Well, your velocity has indeed changed, even if the number associated with those two guys is the same. And here you've kind of accelerated in that direction right there. Your velocity has changed. So let's just take a second right here and take a look at this bug and say that each snapshot in time is a second. And ask yourself, where is the bug accelerating? So pause it for a second and see if you can come up with an answer. Okay, now that you're back, let's just kind of draw this bug's velocity arrows down to the bottom here. So kind of draw this bug's velocity like that. And I'm going to draw it like this. And these guys are roughly the same length because that looks about the same to me. And now this bug is going faster and faster and faster, and maybe even faster right here. And here it looks to me like the bug's going slower and slower and slower, and heck, maybe if it's even stopped right here. So where is this bug accelerating? It is not accelerating in 1 because the velocity is kind of the same. The acceleration is a change in velocity over a period of time. Right over here it looks like it's kind of at the same length, but it's a different direction, so yes, it is accelerating right here. Here it's changing in both length and in direction, so it is right here. Right here the bug is decelerating, so it's going at the velocity vector is a little bit smaller. So let's just get a little bit of practice here. Again, acceleration is going to be a change in velocity per unit time, so meter per second, or meter per second squared. It's going to be the SI unit. example, suppose your car is going 40 kilometers per hour, and about 5 seconds later you measure this instantaneous speed to be 45 kilometers per hour. The change in speed is going to be 5 kilometers per hour, and the acceleration would then be the change in velocity over the change in time. Since these units are kind of dislike, we kind of have to take that into account. Say the acceleration is 1 kilometer per hour second, and we could do some unit conversions if we really wanted to, but I'll leave that as some practice for you. So take a second and give this problem some thought. So when is this guy accelerating? It is when it's slowing to a stop. It is when it's going around a curve. So it's actually going to be both of these. So give yourself a second. Acceleration and velocity are definitely not the same. They are both rates, but they're different quantities. Acceleration is the rate of change of velocity over time, and velocity is the rate of change of position over time, so that one looks good. They're in the same direction. That's not always the case. We could have a velocity in this direction, and we could have an acceleration in this direction right here, in which case something might be slowing down. So it's not going to be this guy. And they're not going to be the same when an object is freely falling. I'll talk about that in just a little bit. So let's kind of move on to a special type of acceleration. So let's start to move into something called freefall. Now, what Galileo did is he's playing around with these ramps or inclined planes, and kind of what he found is the steeper inclines resulted in greater accelerations, greater change in velocity as a function of time. So consider this ramp, and it takes some time for that ball to roll down it. The ball's going faster down here and faster here, and yet faster still. So when the incline was at the vertical, then it was accelerating at the maximum. And what it turns out that Galileo found is all objects are going to fall at the same acceleration as long as it was, as long as we could neglect air resistance. Now this rate of acceleration is quite special, so we're talking about accelerations, and we have a special name for this acceleration. We actually call this little g, which stands for Earth's gravity, and the acceleration in Earth's gravity is actually going to be 10 meters per second squared. Now in reality, if you read a real physics or a more thorough physics textbook, it's actually going to be 9.8 meters per second squared, but rounding off to 10 meters per second squared is going to be good enough for this class. So all objects, all freely falling objects on Earth are going to accelerate at a rate of 10 meters per second squared. You may be asking yourself, does the mass of the object matter? And I have a little demo for that. The answer to the question is no. I've got two objects with different mass, and they both hit the ground at roughly the same time. And if you don't believe me, then I'm a lot heavier than that tennis ball, so I should hit the ground a lot faster than the tennis ball does, and I don't. Now, it turns out that we can kind of calculate the velocity as a function of time for all freely falling objects by saying that the velocity is the acceleration times time. Remember, the acceleration is always 10 meters per second. So consider when the time is equal to 0, well, we would say velocity is equal to acceleration, that's going to be 10, multiplied by time, which is 0. So at 0 meters per second, or 0 seconds, it's falling at 0 meters per second. Maybe at 1 second, we're going to say this is going to be 10 times 1, so at 1 second, and we're talking about a speed of 10 meters per second. At 2 seconds, velocity is going to be equal to 10 times 2, so at 2 seconds, we're talking about 20 meters per second, and then you can easily convince yourself at 3 seconds that it's going at 3 meters per second. So one thing to kind of keep in mind is the difference between here and here is 10 meters per second, and the difference between here and here is 10 meters per second, and the difference between here and here is 10 meters per second. Not surprisingly, that's because the acceleration is 10 meters per second squared. So take a second to chew on this problem. You have an object going 30 meters per second. 1 second later, what should its speed be? Well, you would actually expect it to change by 10 meters per second. Why? Because the acceleration due to gravity is 10 meters per second squared, so you would expect it to be going 40 meters per second. So it's not going to be this one, it's not going to be this one, it's not going to be this one. It has to be this guy right here. Now we can also kind of calculate how far an object has fallen, and we'd simply say that as long as it starts from rest, which it pretty much always will for the purpose of this class, that the distance that it covers is going to be equal to 1/2 times the acceleration times time times time. So we could also even say distance is equal to 1/2 times the acceleration times time squared for shorthand, keeping in mind that the acceleration due to gravity is always going to be 10 meters per second squared. So let's get a little bit of practice using this. Suppose you drop an object down a wishing well, and 4 seconds later it reaches the bottom. How far has it fallen? Well, distance is going to be 1/2 times the acceleration times time squared. So that's going to be 1/2 times 10 times 4 squared, which when you type it into your calculator, it's going to give you 80 meters. So let's just kind of finish off this lecture by just talking about some observations about taking a ball and dropping it. We know that it's always going to accelerate at all times at a rate of 10 meters per second squared. So at any time, right here, we would say that it's accelerating at 10 meters per second squared. So at 0 seconds, at 1 second, at 2 seconds, and at 3 seconds, it's always going at 10 meters per second squared at pretty much every point in its travels. And we've already convinced yourself that the velocity is going to be 0, 10, 20, and 30, all with units of meters per second. And let's just kind of calculate its position. Remember that we would say that its position is going to be 1/2 times acceleration times time squared. You could probably convince yourself that that should be a 0. After 1 second, that's going to be 1/2 times 10 times 1 squared. So that should be a distance of 5 meters. After 2 seconds, that's going to be 1/2 times 10 times 2 squared. So that's going to give us a distance of 20 meters. After 3 seconds, it's going to be 1/2 times 10 times 3 squared. It's going to be 45 meters. So what this kind of says is, while velocity may be increasing at a nice linear rate, 10 meters per second for every second, the position, well, it's covering more and more and more distance the longer that it falls.